Hello, everyone. So in this video, you were just introduced moments ago, the change of basis matrix. What we want to know is what type of important features define this change of basis matrix so that we can recognize them in the future and make it a little easier to compute it. So let's suppose that you have a basis B and a basis C for a vector space V. And let's define an n by n matrix called the change of basis matrix that goes from the basis B to the basis C to be a matrix whose columns is formed by taking the vectors in the basis B, but find their coordinates relative to the C. Those are the columns of the matrix in the order that the basis B is written. This particular matrix has these properties. First off, it's the change of basis matrix. It will send the coordinates of a vector relative to B to the coordinates of the same vector, but relative to the basis C. Also, there's only one such matrix that does that, and it's this matrix you have right here. And lastly, not only is this matrix the only one like it, but it's also invertible. And what's really cool is that the inverse of this matrix is also a change of basis matrix. It just converts the vector's coordinates relative to the C back to the coordinates of X relative to B. So this is a very important thing, and we should really quickly prove it. One of them is easy. I've already done it 2 times now, actually, with numbers. Suppose you have a vector X in the vector space V. You can then take X and expand it in terms of its basis to get the coordinates of V, the coordinates of the vector X. That means that if you want to take that equation on both sides, we can find out what it says in terms of coordinates relative to C, but the right-hand side is a linear combination of vectors in V and the coordinate mapping that goes from the vector to its coordinates relative to C, distributes to constant multiplications and distributes to vector addition. So you get a linear combination of the coordinate vectors instead of the basis vectors. From here, though, notice that the right-hand side can be written as matrix multiplication using our clever little trick we've seen before. So the matrix is the matrix, that's the change of basis matrix that goes from B to C times a vector of coordinates, C1 through Cn. But those entries, C1 through Cn, that's just the coordinates of the vector X relative to B because of the initial linear combination that I wrote down, the one that has the check mark next to it. So that's it. That means then that this matrix is one that converts the vector's coordinates relative to B to the coordinates relative in C. Now we want to know, is this the only one? Is there only one matrix that does that? So let's pretend we have some other matrix out there that converts every single vector's coordinates relative to B to the coordinates relative to C. Let's see if we can figure out what that matrix has to look like. Well, take any vector in the basis B and expand it in terms of the basis B, as I did here for you. Notice that it's a linear combination where all the coordinates are 0, except for the one coordinate in front of ui, which is a 1. This means then the coordinates of ui relative to the basis B is actually just ei. That's important because what I want to know is what's the ith column of this matrix P? Well, the ith column of the matrix P is P times EI. By EI is the coordinates of UI relative to B. But by the defining property of this matrix, that has to be the coordinates of UI relative to C. So therefore, the ith column of this matrix is the ith vector in the basis for U, but relative to C. And that's exactly how I define that matrix, P going from B to C. So there is only one matrix that does this. The columns have to be what you have right here. Now the next one is it invertible? And what would be its inverse? Well, the vectors U1 through UN are a basis for V, so they're instantly independent. But that means that if you look at their coordinates relative to C by the coordinate theorem, those coordinates will have to be linearly independent in Rn, which means by the fundamental theorem of invertible matrices, the matrix that has these coordinate vectors as columns, that would have to be an invertible matrix. So now we know it's invertible. Then after that's really easy. It's a matter of just remember uniqueness. that if this equation here is true, since this guy is invertible, you can take its inverse on both sides. But that means that this matrix is the matrix that sends every single vector's coordinates in terms of C to the corresponding vector's coordinates in terms of B. But there is only one matrix that does that, and that is the change of basis matrix that goes from C to B. So the change of basis matrix that goes from C coordinates to B coordinates has to be the inverse of the change of basis matrix that goes from B coordinates to C coordinates. That's it. Whew, good. So we have those three main results. I think it's important to see it once. It's not very difficult at all. Remember now, the overall idea here is that we have a vector space. That vector space is a vector that's not moving, not changing. It's the coordinates that we're messing with. We're just changing how we represent that vector. We're never actually changing it. So this particular example, this method I've given you, is really easy to use if you're going to a standard basis. I'll show you why. So let's say you have a basis B for P2, which would be 1 plus x, x plus x squared, 1 plus x squared. It's going to be a basis. It's easy to show. Then we'll say E is the standard basis for the same space. I want to find the change of basis matrix that goes from B coordinates to the standard basis coordinates. Well, to do so, take all the vectors in B, find their coordinates relative to E. Those are the columns in the same order. So here are the vectors' coordinates relative to E. And then here is therefore the matrix with those columns. That matrix would have to then be invertible, and its inverse is actually the change of basis matrix that goes from the standard basis to the basis B. So we now have both these matrices. Now you may not believe me. You might go, yeah, I don't believe you, Professor Dugan. Give me some numbers. So suppose we have that change of basis matrix that goes from the standard basis into the basis B for the two bases that I've given you previously. The vector 2 minus x plus 3x squared relative to the standard basis, its coordinates are 2, -1, and 3. 2 times 1 minus 1 times x plus 3 times x squared. That's the vector 2 minus x plus 3x squared. So let's find out what its coordinates are relative to B. So to find the coordinates relative to B, that would have to be equal to the change of basis matrix that goes from E to B times the coordinates of this vector relative to E. It's just a matter now just bashing out this particular multiplication. The change of basis matrix times the coordinates, that has to then be the coordinates of the vector relative to B. And that vector then is -1, 0, 3. Now we can check it too, because we have the basis B. So then I can then go ahead and form the linear combination based upon these coordinates and see if we get the original vector back. So then if you take the linear combination of -1 times the first vector in B, plus 0 times the second vector in B, plus 3 times the third vector in B, you get the same vector, 2 minus x plus 3x squared, because you have to. All I'm doing is taking the vector v in P2, 2 minus x plus 3x squared, and all I'm doing is giving it two different representations. I'm not changing the vector. I'm not moving it at all. All right, good. So you have that basic idea. So then what we need is a better way to compute it, though, because very often we don't go from a basis to the standard basis. If we did, it's easy because I just showed you how to do so. Or even to go from the standard basis to just a general basis. It's just the inverse of the other one. I'd like to make that faster. So then to do so, we're going to show you a little trick. Something you've seen before, it's just never been presented to you this way, but you have seen this trick before. So you have the vector space V. You have a vector X in it. Now, by the coordinates relative to B mapping, that vector X gets mapped to a vector in Rn. The coordinate mapping relative to the basis C maps the vector X to another vector in Rn. I want to go and find the mapping that goes from here to there. So to do that, we're going to introduce another basis. We're going to use a stepping stone. This will be the standard basis, E. Any basis actually works. You can use any basis you like, actually. We're just using E because it's frankly easier to understand. So here's our standard basis. Okay. So there are coordinates of X relative to the standard basis. That's also an Rn. All these coordinates are an Rn. But it's really easy to find the transition matrix or the change of basis matrix that takes the vector's coordinates relative to B to the coordinates relative to E. There's also a really easy change of basis matrix that take the coordinates relative to C and converts it to the coordinates relative to the standard matrix, the standard basis. But that last matrix is invertible, so I can find a change of basis matrix that goes from the standard basis coordinates to coordinates relative to C. The way you look at it is you could either go directly there via this mapping with one matrix multiplication, or you could do a sequence of two matrix multiplications to get to the same place. So with that idea, that then gives you this basic theorem, which I'm not proving symbolically. I'm choosing to just go ahead and just give you the result. So if you have a basis B and a basis C of a vector space, and E is now any other basis, it doesn't have to be the standard one. We almost always use the standard one, but it can be anything. Then if you want to know the change of basis matrix to go from B to C, find the change of basis matrix that go from B coordinates to E coordinates, the change of basis matrix to go from E coordinates to C coordinates, and then if you just multiply this to that, you get this one. Notice how the arrows imply the end result. That's why the arrows are there to help you out. But more importantly, we know though how to compute this one because it's just the inverse of that one. And if we're using the standard basis, this matrix is easy to find, and this matrix is easy to find if E is the standard basis for the vector space. But I can go further because this actually directly connects to a technique or a little trick I showed you before. Do you remember if we wanted to find the inverse of A, we would write down A and then the identity matrix and then row reduce it? When you did so, you would get the identity here and the inverse is there. Well, you can generalize the exact same result. It's the exact same proof, in fact. It's just not something we ever needed. That if you take the matrix A and the matrix B and row reduce it, assuming that A has an inverse, the left-hand side would become the identity, and the right-hand side of that line would then be A inverse times B. So if you want to find out the inverse of this matrix times that matrix, that's what A is and what B is. The technique is here is A, here is B, row reduce it. The left-hand side has to become the identity, and the right-hand side has got to be this product, which is the thing that you want, which is right there. Neat, right? Neat. So then it's really, really easy actually to go use our computational power we've built up in Rn to find the change of basis for B coordinates into C coordinates. I'll show you what I mean. I'll do an example. It's not difficult at all. So here's two weird bases for P2. So then the change of basis matrix to go from C to E is just take all the vectors in C, find out what they are relative to the standard basis. That's the columns. The standard matrix, the change of matrix, the change of basis matrix that goes from B coordinates to E coordinates. Just take all the vectors in B and find out what their coordinates are relative to the standard basis E, and that's the columns of that matrix. Then to find the change of basis matrix to go from B to C directly and to not use these two matrices, what we do is we have to form an augmented matrix where the first change of basis matrix going from C to E is on the left. The change of basis matrix that goes from B to E is on the right. That's the left and the right. And then we just row reduce it. This will then be what's left over, the change of basis matrix to go from B to C. Notice, do you see how the B is here and the C is there? See how the B is here and the C is there? Again, the notation is there to help you remember the results. Let's just crank it out. Here is the two matrices adjoined side by side, and I row reduced it. The right-hand side of that line then has to be the change of basis matrix, going from B coordinates to C coordinates. And we could check it if you really want to, because here is some vector in P2. That vector is 5 plus x plus 2x squared. Now the coordinates, by looking at the linear combination, the coordinates of V relative to B is 2, -1, 3, because those are the scalars used in the linear combination. But that means then I can then figure out the coordinates relative to C. There's a typo here. That should be a C there, not E. C there. And that's found by just taking this coordinates relative to B and multiply it to the change of basis matrix. It goes from B coordinates to C coordinates. And doing that multiplication, you get the vector 4, -1, 2. So we can check our work too, because we know what the basis C is. So I can form a linear combination from the basis vectors in C using the coordinates, using the scalars 4, -1, and 2. And by doing so, notice you get the exact same vector. Because you have to, because we're not moving that vector. We're not moving vector V. We're just changing the way it's represented. It's like sometimes people call you Joe or Bob or Biff or your other nicknames, depending upon who you are, right? So you don't change, but how you refer to might. And being called different things can help in different contexts. I believe that's enough for that video.